loading moment and also loading is a torque. I know the range of these two values. And also yield strength material, yield strength SE. And how can I use the DET? This equation is based upon the DET. DET is Lomices yield criteria, and DET end is a Goodman theory. All right? So I'm going to give you one example. So this example is so suppose we have the real wheel drive car, so accelerates around a bend at high speed. So the drive shafts are subjected to bending and torque. We have bending, and also we just have a twist and torque. So the acceleration torque T is reasonably constant at 400 Newton meter. So this is a Newton meter, so international unit. Well, the bending moment is varying due to the concerning and is expressed in Newton meter. So this is the bending moment. And even though the torque is constant, but the bending moment is cyclic. You understand, guys? Because the sine function, it is periodic function. Do you guys agree? So that means my M in bending moment is changing from lower value, which equals 250, to the highest value, which equals this guy plus this guy, when sine equals 1, right? And sine is changing from, sine is changing from negative to positive. So minimum will be 250 minus 800. Maximum will be 250 plus 800. So that means the bending moment, this is cyclic loading, right? Do you guys agree? Okay. Now, to fight this MM, so is MM equals 250. Okay, so 250 mean is 250. The alternating is 800. And how to do that? MM equals this. MM equals. Still remember, MM equals maximum plus minimum. And MA equals maximum minus minimum. Right? So this is the maximum max equals 250 plus 800. So one side equals 1. Minimum equals 250 minus 800. So I can use these two equations get M and A. So I also know the torque. Okay, the torque is a constant. The torque is a constant. That means that the torque M equals T. Right? Does that? Because this guy constant, and my TA equals 0. Here there is no range. It's because this guy is constant. So we want to use this equation. Using this is the shaft. We calculate the shaft diameter using the MSST. That this equation. I'm going to show you guys. So first, this is the axle load. This is I'm sorry. So bending moment. You can see SE prime, and we can. I will. If I give you an example, I'll give you a homework. I'm going to tell you what is the factor you should use. But for this one, we check this equation, and based on this table, SE prime, and we use 0.5 multiplied by SU. So this is we can calculate SE prime, and then I'm sorry, you can look at the figure. Okay, so usually I will give you this equation. I test you. And this is size factor, and this size factor Ks, lowercase ks, because we have a hierarchy, capital Ks, and lowercase ks, and lowercase ks, and equals, and using this equation. So this is point 0.869, and B, the power is negative 112. So for this one, and the D is 0.3 inch less than the D less than the 10 inch. Okay, I want you guys to write down. If this is your D, the range, look at this one, this inch, okay? And you are supposed to use this equation. The D is equal to 1, Ki is equal to 1 if the D is less than 0.3 inch or and D is less than 8 millimeter. So this is 0.3 and 8, and so this is 8 inch. 0.3 inch and 8 millimeter is almost equivalent. But however, if you are using the millimeter and you are supposed to use this equation 1.189 and D negative 0.112. Now this time, and so this is 8 millimeter and to 250 millimeter. So be careful. Why should I use this one? Why should I use this one? If you are using inch, use this one. And if you are using millimeter, use this one. So this is how we calculate the size factor Ks. Can you see this one? I'm sorry, maybe you cannot. Right? Clayton, can you see? I'm sorry, I'm going to, no worries, I'm going to take a photo. Sorry guys. So we see we can use this equation and to calculate, okay? So assume. So sometimes, and we are mechanical engineer, when we design something, because especially when we design new things. So we do not have anything and to depend upon. So what should we do? We just pat our head, okay? Pat our head and make a reasonable, realistic estimation. So we just at the very beginning we just assume the D equals 30 millimeter, and then we based on this equation, and we calculate this Ks. I will get this Ks, and then we just suppose 99% probability of survival, reliability. We talk about this reliability. Then this reliability Kr equals 0.82. So this is reliability, the Kr, the 0.82. And then we just use this equation, okay? ICE, this is actual practical endurance limit, it equals the theoretical endurance limit multiplied by safety, this is a factor Kf is the size, the Kr. And Ki is the size, we just assume Kf equals 1. So this is Kf. I will give you the Kf. Kf is the surface because the surface finish. And so based on this equation, we can calculate ICE, right? And then we just go here this equation, and we will have so this because the Tm we only have Tm here and Ta equals 0. Right? And then we can use this equation and the safety factor we assume 0.5. So this is our the value, the D, the value for the first iteration. For the first iteration. Right? And then we need to do to check. We need to come back to check, okay? To check guys. And we get this new D, and then we come back to see the safety factor and put this safety factor here, and then we get this new Ks, right? And the probability, this is a surface finish factor does not change. So this Ks changes the new value, and the 0.82 is the Kr, reliability factor, which is not changing either, and still get this IDE prime, and then we put it here, and we can get this D. The D, so this is new D, the second iteration. This new D is this one. So you can see this one is very, very similar to our previous one. 0.7714. This is 7714. So this is 7739. I'm sorry. So here, this is a 79. So what does that mean? It means that, guys, you should stop, and you should have a value when these two p-values they are very, very close. If they are very close, we say it's convergent. You understand? One more time. When should we stop? And we pat our head and get the estimate. And at the very beginning, estimate value 30 millimeter. And then we do this first iteration, get this value. And then we do the second iteration, get the second value. If these two values, they are very, very close, and we can stop the iteration. And we can say, this is the D that I recommend to my customers. Okay, so pay attention to this one. I will post this one online, and this is very useful. So this is the procedure can be applied to all other the sets of equations. And then I'm going to talk about this is the homework. And I talked about this one last time. Today I'm going to talk about this two. I'm going to give you more hints. So for first problem, how can we solve the problem? Yes, by the way, as you can see, based on this problem, you can see you can use the Eisen diagram to do a lot of calculations in our daily life. The jack. Have you guys ever used the jack to lift out your cars? Yes, right? And then you can just estimate and how when your jack will break. Right? It's very, very interesting. So here, how to do that, guys? Here is the jack for mechanism. You can see, I'm not ready. The maximum compressive touch stress in the jack is 190 megapascal when this car is jacked up so high that both wheels are in the air. So the load on the jack is 8,000 Newton. Now, I want to load the jack to 17,000 Newton. I want you guys to tell me how many times this jack can be used. So how to solve the problem is, so I'm going to give you some hints. So first of all, which SU, I give you the SU. I give you the SU. SU equals 650 megapascal. And SY is given also on 380 megapascal. You use the Eisen diagram. So we know that 8,000, if I have 8,000 Newton, and then my maximum compressive stress is 190 megapascal. Right? And then what about is a 1,700 Newton? 17,000, I'm sorry, 17,000 Newton. So what is the stress? What is stress?
You compute the ratio.
Yeah, compute the ratio, right? So these we just say this guy over this guy equals this equals this over this, right? And then I can have the sigma is proportional, and sigma equals this is 17,000 multiplied by 190 megapascal and divided by 8,000 Newton. You guys agree? So here, this it gives me some value. I will give these values to you. Right? You calculate it. And then this is axial loading because this is axial loading compression, even the compression. The axial loading SE prime, and it equals, and we use this factor for the 45 multiplied by SU, and you get another value SE prime. Okay? So this is SL prime axial loading. This is axial loading. Because axial loading. And SL prime, and we will use this factor, axial loading, multiplied by SU. So we have this value. Make sense? And then BS. The BS, the slope BS, it equals 1/3 minus. Always pay attention to this minus. And this is a common log SL prime over SE prime. So, and you have this value. And then you can use this as NT. Use the equation for this NT and to calculate this value. Okay.
How would we use the SN diagram in this case then?
Huh?
Could we use the like SN diagram instead of that equation, or like just?
Yeah, this equation is based on SN diagram.
Oh, it is. Okay, you don't just like look at the diagram.
Yeah.
Okay, great.
This equation, they are based upon the SN diagram, right?
Okay.
SN diagram, it means that this is my straight line. So here, is 10⁻³ and SL prime. So here is 10⁻⁶ SE prime. So these two independent points describe my straight line. So then, for any points here, I can get this guy's corresponding is NT. Okay? So I will write this one, you write this one NT, and then you just plug in this sigma, okay? This is sigma, and this sigma is your SF. Then you finish it. Okay, second one. And second problem is kind of tricky. And second problem is kind of tricky. Why is it tricky? And because this is a hole, and the stress, the biggest maximum stress is here. Do you agree? So when you calculate the stress, and don't use this cross-section area, and you are supposed to use the cross-section area that has a minimum value, and which is here. So I give you this is the vector KF, surface finish, and KF equals this one. KS is the size factor, KR reliability, and KT is the temperature, and KM miscellaneous. All other factors are equal to 1. So only this one for the 86. And so what you are supposed to do, guys? And so the fluctuating, the problem 2. The fluctuating, this is from 8,000. I'm sorry, 800 and to 3,000 the pound of force. Now this time, right? This time, this is a sigma m alternating and sigma a and sigma. This is a sigma maximum minus sigma minimum So here is sigma maximum plus sigma minimum. And for this one, right, be very careful. And the sigma maximum equals 3,000 on the force divided by the area. And what is the area? Now the area, okay, so the area at the whole. So what is the area? AH equals the thickness is 3 inch. However, the length is this. So this 1 minus 1/4. Okay? So this equals multiplied by 1 minus 1/4 inch. So because this is a hole there. Now, if you have this one, and so you can just plug in sigma minimum equals an 800 pound of force divided by AH. And be very careful about the units. And then you can just use the KF. So this is Goodman theory and capital KF. So this is capital KF. I talk about lowercase KF, and lowercase KF is a surface finish factor. So capital KF is a stress concentration factor. So this one multiplied by sigma A and divided by SE plus sigma M SUT equals 1 over NS. So this is the Goodman theory. So, guys, ICE prime. So this ICE prime ICE prime equals 0.45 SU. Why? Because it's isoloading. Isoloading, right? It's isoloading. ICE prime. And then SUT. SU and SUT is the same. So how to get the ICE prime? Then how to get the SE? SE equals SE prime multiplied by KS, KF, and KT, and KM. So see all these values are given. And KF is given KS, KT, KM, and all they are equal to 1.0. And also KR, yeah. You can get the SE prime. Questions? So for this one, you can calculate this NS equals NS is a safety factor. And so this equation says that if we want if we want this specimen to have infinite number of cycles before it fails, what is the safety factor? So if this safety factor is greater than 1.0, that means our design is good. Questions for these two problems? Question? No question? Let's move on to our next one. So next one is a flywheel, okay, flywheel design. And flywheel design, the given conditions And output, the load torque is given. And load torque in a punch press, the punch press for each revolution of the shift is given this. So here this is so this is a torque, and so this is a theta. I know that here is a pi, here is 2/3 pi. So here is a pi, and here is a 2 pi. Here is the 12, and then going up. Is 144. So here is a 12 from 0. This is a 12. This T is a Newton meter. So this is how the torque. This is 1 cycle. Okay, 1 cycle. The coefficient of fluctuation. Fluctuation is 0.05 about of average speed. On 600 RPM. Assume the flywheel solid state. This is a solid state. A solid disk. And it made of low carbon steel. Low carbon steel. And the thickness equals on 1 inch. And so what we are asked to do is first, the average load. Or the output torque. So second, the location. And theta omega maximum and theta omega minimum. And the third one is the energy required. The fourth one, the outside diameter of the flywheel. The D of the flywheel. Okay, last time I talked about the procedure and how to design the flywheel. Just to remember, and the torque. The flywheel, I told you, flywheel is very the precursor of this the battery. We can treat this one as a battery. If we have more energy, we can store the additional energy onto the flywheel. If we need energy, And we can ask the spread wheel to release some energy, so we can use. How to solve the problem? On first one. So the average, okay? So our average, how to calculate? Average we use. This is a 2 pi, okay? So T2 pi is a cycle, is a time. And the 2 pi multiplied by the T average, we call TL average. So this equals 12 multiplied by pi, okay? 12 multiplied by pi is 0. And then 144 plus 144 multiplied by is a half pi. The duration is half pi. And this duration is half pi. And then we take another one, another also is a half pi multiplied by 12. You understand? And this is how we average. So this is a torque for the duration of one revolution. 2 pi, I mean 360 degrees. So we can get, so this one gives us a TL average is a 45 Newton meter. And then look at the B, right? B, so theta omega maximum and theta omega minimum. What is theta omega maximum? So this is theta value at which we have the maximum omega. And for here, so this is the pi. Okay, so for our case, the change. That is the spike. This is the transition. And this is theta omega maximum equals pi. It means that it is at this point that I have a transition from the lower and to the maximum value. Transition, that is very important. Otherwise, some students say, I don't know why we don't see theta at this point. Right? The transition. So the theta W minimum means that why I go down, right? What at which the theta value at which I goes down. And so this equals 3 pi over 2. So these are two values. And C. And for the C, for the third part, C. So the kinetic energy, okay, so for the equation, based on the equation, the kinetic energy from one cycle, so this is KE. KE equals negative sign. Remember this negative sign is, so here is a theta minimum, omega minimum, and theta omega maximum. And then we have TL minus TL average and D theta. Right? And for our case, guys, because theta omega minimum is 3 pi over 2. So this is C omega maximum is a pi. So we can have so this one, the TL and TL is a 144 minus TL average, which is 45, and we can have 144 minus 45. The duration is half pi. So this gives us 155 and 0.5 Newton meter. So this is the energy. Then we look at the last part, the D part. For the D part, guys, so the average angular speed, the average angular speed this is the omega average and equals, okay, so because the omega is given as the 600 revolution per RPM, right? RPM is not a standard one, so it equals 600 RPM. RPM means this one, right? You guys agree? Revolution per minute. I need to change this guy to radian per second. And how can I do that? So here is 1 minute and 60 seconds. R is revolution, right? Revolution is a 2 pi one revolution. So if we use this one gives us 62.83 radian per second. So you have got to convert this one otherwise, and your answer will be totally off from what it's supposed to be. And we use the standard units. Questions? No? No questions? Then based on equation 11.72, the IM. What is IM? IM is mass moment of inertia. Last time I told you. Mass moment of inertia. It is not related to the geometry, but also related to the mass. Mass means the density. Okay, so this equals, and Ke is the kinetic energy we just got, and divided by Cf. Cf is the coefficient of fluctuation of your torque, and then multiplied by omega AVG average and squared. So you just plug in 155.5, and the CF equals 0.05, and then multiplied by this value you just converted, and 62 and 0.83. So this gives you 0.78 and 79 and kilogram meter squared. You can see mass is there, geometry is there. And then we know that, okay, so IM, and for solid mass moment inertia, it equals MA is the mass of the disk, the D squared, and divided by 8. And then, what is the mass? The mass equals the solid, okay, solid disk. How to calculate mass? Mass equals pi d power 2 divided by 4. That is the cross-sectional area, right? Cross-sectional area multiplied by the thickness, the volume, and then multiplied by rho. So this is my MA, okay? So this is my mass of my disk. And then I just D squared 8. So this is my MA. And so you can just simplify this one, you will get pi over 32 rho and d power 4 multiplied by the th. Th is the thickness of your this is your th. So we know that rho equals 7860 and kilogram and per the cubic meter. Then because this is IM, then this is IM equals, and you just plug in, okay? And you just plug in everything pi. Let me finish. And 32 and 7860, then and 0.0254 and p power 4. What is this, guys? Because it is inch, 1 inch. 1 inch, okay? This 1 inch, you need to convert it to a meter. You understand this? This is my meter. In a meter. Otherwise, and you have US customer units and also international units, your answer definitely will be wrong. No doubt. You need to convert here. That's the reason I have this is the conversion factor here. So D power 4. So this equals 19.60 and D power 4. This is 1 inch. 1 inch. 1 inch needs to be converted to this value in meter, because they are written in meter. So this one equals this. Right? So one equation and one unknown, we can get this D. And this D, and I will give you this task to calculate D. Okay, so that's all.